welcome. In this lesson, we are building a foundation for naming organic compounds without guessing. A lot of students treat organic names like random words they have to memorize, but that is not really the best way to learn it. An IUPAC name is basically a code. It tells you the main carbon skeleton, what functional groups are present, where they are located, and sometimes the 3D arrangement. The goal of this video is to give you one decision process that you can reuse again and again. We are going to start simple, then build up to functional groups, common traps, and practice problems. Before we start naming examples, here is what this lesson is meant to teach. First, I want you to be able to read a name instead of seeing it as one scary long word. You should be able to spot the parent, prefixes, numbers, suffix, and stereochemistry. Second, I want you to name a structure by following the same order every time. That order is boss group, parent chain, numbering, prefixes, and then any final details. Third, I want you to avoid the common traps that show up on quizzes, like choosing the wrong parent chain or numbering from the wrong end. Organic names exist because chemists need a clear way to communicate structures. If I say a random common name, there might be confusion. But if I use a systematic name, the name should tell you what the molecule looks like. The carbon skeleton tells you how many carbons are in the main chain or ring. The functional groups tell you what kind of molecule it is, like an alcohol, aldehyde, ketone, acid, ester, amide, or amine. The numbers, called locants, tell you where those features are. In more advanced examples, stereochemistry tells you the 3D arrangement. So naming is really a map from words back to structure. Let us look at the example name on the slide, 4-methylhex-2-on-1-ol. This looks complicated at first, but it breaks into pieces. The number 4 tells us where the methyl group is. Methyl is the prefix, meaning it is a branch attached to the parent. Hex tells us the main parent chain has 6 carbons. The 2N part tells us there is a double bond starting at carbon 2. The 1-ol part tells us the alcohol group is on carbon 1. So the name is not random. It is giving structure information in a specific order. Once you learn the pieces, long names become much easier to read. This is the main roadmap for the whole lesson. Use this order every time. First, find the boss functional group. That means find the group that gets priority and usually controls the suffix. Second, choose the parent chain or ring. Third, number correctly, starting from the end that gives the important feature the lower number. Fourth, add substituents and prefixes like methyl, bromo, hydroxy, or oxo. Fifth, add unsaturation and the suffix like ene, yne, ol-al, 1, or oic acid. Finally, add stereochemistry last if the drawing gives enough 3D information. This order prevents most naming mistakes. A lot of students start with the wrong approach. They look for the longest chain first, then try to use the smallest sum of numbers, then guess what the ending should be. That works sometimes for very easy examples, but it breaks down fast. The correct approach starts with priority. Ask what functional group is in charge. Then choose the longest valid parent that includes the important group. Then number by priority, not just by arithmetic. After that, add prefixes and the suffix. Stereochemistry comes after the flat structure is already named. The big idea is this: naming is not about guessing what sounds right. It is about following the rule order. These 4 words are the basic language of nomenclature. The parent is the main skeleton. It is usually the main chain or ring that gives the base name, like butane, hexane, cyclohexane, or benzene. A prefix is something attached to the parent, like methyl, bromo, hydroxy, or oxo. The suffix is the ending that usually shows the main functional group, like OL for alcohol, Al for aldehyde, 1 for ketone, or OIC acid for carboxylic acid. A locant is a number that tells us where something is. So when you see a long name, do not panic. Break it into parent, prefixes, suffix, and locants. You will also see common names and retained names. For example, acetone is a very common name, but the systematic name is propan-2,1. Acetic acid is very common, while ethanoic acid is the systematic style students often learn. Some names are officially retained in certain contexts, so they are not just random nicknames. The important point is that you should recognize both forms when studying. In a strict naming question, your instructor may want the systematic IUPAC style answer. In a lab or textbook, common names still appear a lot. So do not ignore common names, but do not rely on them as your only naming system. Now we start step 1, find the boss functional group. I am using the word boss because it is easy to remember. The boss group is the group that usually controls the suffix and often controls the numbering. For example, if a molecule has a carboxylic acid and an alcohol, the acid is usually in charge. The alcohol does not disappear, but it becomes a prefix instead of the main ending. This is why we have to identify priority before we choose the chain or start numbering. This is a simplified functional group priority ladder for an intro naming lesson. At the top are carboxylic acids and important acid derivatives like esters and amides. Then come nitriles, aldehydes, ketones, alcohols, amines, alkanes, and alkenes, and then groups like ethers and halogens that usually act as prefixes. The exact official IUPAC tables are more detailed, but this ladder is enough to understand the beginner pattern. The highest priority group usually becomes the suffix. Lower priority groups usually become prefixes. So if an alcohol and a carboxylic acid are both present, the acid becomes the main ending and the alcohol becomes hydroxy. This is one of the biggest ideas in naming. This example shows why priority matters. The structure is HOCH, 2 degrees Celsius, H, 2 degrees Celsius, OOH. There is an alcohol group and a carboxylic acid group. If we tried to name both as main endings, the name would become messy and incorrect. The carboxylic acid has higher priority, so it controls the suffix. That gives us propanoic acid as the parent acid. The OH group is still there, but because it is lower priority in this molecule, it becomes the prefix hydroxy. Now we number from the acid carbon as carbon 1, so the OH is on carbon 3. The correct name is 3-hydroxypropanoic acid. This is a common student trap. When a molecule has more than one functional group, students sometimes try to give every group its own main ending. But most polyfunctional names need one main suffix boss. Other groups are usually described as prefixes. That is why an OH group can be alcohol in one molecule, but hydroxy in another molecule. It depends on what else is present. A simple memory cue is one suffix boss, other groups become accessories. This does not cover every advanced exception, but it is the right foundation for intro-organic naming. Now we move to step 2, choose the parent. This is where the phrase longest chain can be misleading. The parent is not always just the longest line your eyes can trace. It has to be the longest valid parent according to the priority rules. In many cases, that means the parent must include the carbon attached to the boss functional group or the carbon that is part of the boss group itself. So before you count carbons, ask whether the chain you are choosing is allowed. Here is the better version of the longest chain rule. First, choose a parent that includes the suffix-bearing group whenever possible. Then, from those valid choices, choose the best parent, often the longest valid chain. This matters because students often choose a chain just because it visually looks long, but a chain that leaves out the important functional group is not valid. For example, an aldehyde carbon must be part of the parent. An alcohol suffix needs the parent to include the carbon-bearing OH. So parent selection is not just a drawing exercise, it is a priority exercise. This is one of the best trap examples. The structure is CH 3 degrees Celsius H with a CH 2 degrees Celsius H3 branch, then CH 2 degrees Celsius HO. A student might look at part of the structure and call it 2-ethylbutanol. That sounds reasonable at first, but it is not the correct parent choice. The aldehyde group is CHO, and that aldehyde carbon must be included in the parent chain. When we trace the longest valid chain that includes the aldehyde carbon, we get a 5-carbon parent, so the base is pentanol. The remaining branch is a methyl group on carbon 3, so the correct name is 3-methylpentanol. This shows why longest valid parent is better than just longest visible chain. Step 3 is numbering. Once the parent is chosen, we have to decide which end is carbon 1. The main idea is priority beats arithmetic. A shortcut, like smallest sum of numbers, can work in easy examples, but it is not the full rule. The most important feature should receive the lowest number first. That usually means the principal suffix group, then unsaturation, then substituents. So before you start counting, ask what feature is most important. The slide shows the simplified numbering priority. First, the principal suffix group matters most. For example, if alcohol is the suffix, the OH-bearing carbon should get the lower number. Second, unsaturation matters, meaning double and triple bonds need locants. Third, substituent prefixes get numbers, like methyl or bromo. If there is still a tie, you move to first point of difference and other tiebreakers. The exam warning is that smallest sum is only a shortcut. If you use it without thinking about priority, you can number from the wrong end. Always ask what feature controls the name first. This example is CH, 3 degrees Celsius, HOHCH, 2 degrees Celsius, H, 2 degrees Celsius, H3. The parent has 5 carbons, so it is based on pentane. The OH group makes it an alcohol, so the suffix is O. Now we choose the numbering direction. If we count from the left, the OH is on carbon 2. If we count from the right, the OH would be on carbon 4. Since the OH is the suffix-bearing group, it must get the lower number. So the correct name is pentan 2-ol, not pentan 4-ol. This is a clean example of priority beating a random numbering direction. Now that we have the core rule order, we can start with hydrocarbons. Hydrocarbons contain carbon and hydrogen, and they form the basic skeleton for many organic names. We will start with alkanes, then move into branches, alkanes, and alkynes. This section is important because even when a molecule has functional groups later, you still need to recognize the carbon parent. If the carbon skeleton is wrong, the whole name usually becomes wrong. Alkanes are saturated carbon chains. Saturated means the carbons are connected by single bonds only, with no double or triple bonds. Alkanes use the ending ane. The root tells you the number of carbons, meth for 1, ete for 2, prop for 3, but for 4, pent for 5, hex for 6, and so on. The example on the slide is CH, 3 degrees Celsius, H, 2 degrees Celsius, H, 2 degrees Celsius, H3. It has 4 carbons, all single bonds, and no branches. 4 carbons gives but, and a saturated chain gives ane. So the name is butane. Now let us add a branch. The structure is CH, 3 degrees Celsius, H, with a CH3 branch, then CH, 2 degrees Celsius, H3. First, there is no special functional group, so we look for the parent carbon chain. The longest continuous chain has 4 carbons, so the parent is butane. Next, we number from the end that gives the branch the lowest number. The branch is a methyl group, and it is on carbon 2. So we put the locant first, then the prefix, then the parent. The final name is 2-methylbutane. Notice that the branch is not part of the parent name. It is named as a prefix. When there is more than one substituent, we need locants for each one, and we usually list substituents alphabetically. In the example 3-ethyl 2,2-dimethylheptane, the parent is heptane. There is an ethyl group at carbon 3 and 2 methyl groups at carbon 2. The important alphabetizing rule is that prefixes like di, tri, and tetra do not control alphabetical order. So dimethyl is alphabetized as methyl, not as dimethyl. Ethyl comes before methyl because E comes before M. That is why the name starts 3-ethyl before 2. 2-dimethyl. Now we move from single bonds to multiple bonds. Alkanes contain a carbon-carbon double bond and use the ending E. Alkanes contain a carbon-carbon triple bond and use the ending Y. The multiple bond must be inside the parent chain, and it needs a locant, CH2, double bond, CHCH. 2 degrees Celsius, H3 has 4 carbons, and the double bond starts at carbon 1, so the name is but 1 and N. CH 3 degrees Celsius triple bond, CCH3 has 4 carbons, and the triple bond starts at carbon 2, so the name is but 2-wine. Modern IUPAC style places the number right before the ENA or INA part. This example is CH 3 degrees Celsius H double bond CHCH with a CH3 branch, then CH 2 degrees Celsius H3. First, the parent must include the double bond. The longest chain that includes the double bond has 6 carbons, so the parent is hexene. Now number the chain so the double bond gets the lower locant. From the left, the double bond starts at carbon 2. From the other direction, it would start later. So we keep this numbering. The methyl branch is on carbon 4. Put it together. Methyl at 4, 6 carbon parent, double bond at 2. The final name is 4-methylhex-2-ene. The alkyne example is CH, 3 degrees Celsius H, 2 degrees Celsius triple bond CCH with a CH3 branch, then CH, 2 degrees Celsius H3. The parent chain has 7 carbons and includes the triple bond, so it is based on heptene. Now we number to give the triple bond the lower locant. The triple bond starts at carbon 3. There is also a methyl group on carbon 5. So we write the substituent first, then the parent, with the triple bond location. The final name is 5-methyl-hept-3-ne. The key idea is that the triple bond stays inside the parent and receives a clear number. Now we move into oxygen-containing functional groups. These are extremely common in organic chemistry, and they are where priority becomes more important. We will look at alcohols, aldehydes, ketones, carboxylic acids, and esters. Each group has its own naming pattern, but the same roadmap still applies. Find the group in charge, choose the parent, number correctly, and then build the name. The slide shows 3 common oxygen families. Alcohols contain an OH group. When alcohol is the principal group, the suffix is OL, as in propan-1-ol. Aldehydes contain a CHO group at the end of a chain. The aldehyde suffix is al, and the aldehyde carbon is automatically carbon 1. An example is ethanol. Ketones contain a carbonyl group inside the chain, and the suffix is 1 when the ketone is principal. CH 3 degrees Celsius O, CH3 is propan-2,1, also commonly called acetone. These names are important because oxygen groups often control both the suffix and the numbering. This example has both an alcohol and a halogen, BrCH 2 degrees Celsius HOHCH3. The OH group is the boss group here, so the parent is propanol and the suffix is OL. We number from the end that gives the OH the lower number. The OH is on carbon 2 either way in this 3-carbon chain, so then we place the bromo group with the lowest possible number. Bromo is on carbon 1. The final name is 1-bromopropan-2-ol. The important idea is that halogens are prefixes. They do not control the suffix over an alcohol. Carboxylic acids are very important because they usually outrank many other groups. A simple open-chain carboxylic acid uses the ending OIC acid. In CH, 3 degrees Celsius H, 2 degrees Celsius OOH, there are 3 carbons including the acid carbon, so the name is propanoic acid. Esters are named differently. An ester has an oxygen side and an acid-derived side. You name the oxygen side alkyl group first, then the acid-derived OAT part. For CH 3 degrees Celsius H 2 degrees Celsius OOCH3, the oxygen side group is methyl and the acid-derived part is propanoate. So the name is methylpropanoate. For esters, reading the 2 sides correctly is the main skill. Now let us name a branched ester, CH 3 degrees Celsius H, with a CH3 branch, then CH 2 degrees Celsius OOCH3. First, split the ester. The group attached to the single bond oxygen is methyl, so methyl comes first. Then name the acid-derived side. The carbonyl carbon is carbon 1, and the acid side has 4 carbons total, so it is butanoate. There is a methyl branch on carbon 3 of that acid-derived chain, so the acid side is 3-methylbutanoate. Put the oxygen side first, then the acid side. The final name is methyl 3-methylbutanoate. Next, we move to nitrogen-containing functional groups. The 2 main ones in this deck are amines and amides. Students often confuse these because nitrogen can be part of the main functional group, or it can carry substituents that need special labels. The most important thing to watch for is whether a substituent is attached to carbon or directly to nitrogen. If it is attached to nitrogen, the name may need an N label. Amines can use the suffix amine when they are the principal group, like butan-1-amine. If another higher priority group is in charge, the amine can become the prefix amino. Amides are different because they come from carboxylic acid derivatives and use the suffix amide. In the example N-methylpropanamide, the parent is propanamide. The methyl group is not attached to a carbon in the parent chain. It is attached to the nitrogen. That is why the name uses N-methyl. The letter N tells the reader that the substituent is on nitrogen. That is the main takeaway for amides. Now we combine 2 topics students often see later, aromatic rings and stereochemistry. Aromatic compounds often involve benzene rings. Sometimes benzene is the parent, and sometimes the ring is a substituent called phenol. Priority decides what role the ring plays. For simple desubstituted benzene compounds, you may see ortho, meta, and para, but numbers are more general and safer. Stereochemistry comes after the flat structure is named. E and Z describe double bond geometry using priority rules. R and S describe chiral centers, but you need a real 3D drawing to assign them correctly. In this aromatic example, the ring has a carboxylic acid group, a bromo group, and an amino group. The carboxylic acid has high priority, so the parent is based on benzoic acid. That means the carbon attached to CO2 hours is treated as position 1. Then we number around the ring to give the substituents correct positions. The amino group is at carbon 4, and the bromo group is at carbon 3. Alphabetically, amino is cited before bromo. The final name is 4-amino-3-bromobenzoic acid. The ring still follows the Boss group rule. Here is a fast mistake correction round. Mistake 1 is the longest chain trap. 2-ethylbutanol looks tempting, but the correct name is 3-methylpentanol because the aldehyde carbon must be included in the parent. Mistake 2 is wrong numbering. Pentan-4-ol is wrong when pentan-2-ol is possible because OH controls the numbering as the suffix group. Mistake 3 is alphabetizing dimethyl under D. Ignore D, tri, and tetra when alphabetizing. Mistake 4 is relying only on common names. Acetone is useful to know, but propan 2,1 is the systematic form. Most mistakes come from using the rules in the wrong order. Now pause the video and try these 3. For the first one, look for the positions of bromo and methyl. For the second one, remember that OH controls numbering because alcohol is the suffix group. For the third one, watch where the methyl group is attached. If the methyl is attached to nitrogen in an amide, you need an N label. Do not rush these. Use the roadmap, Boss group, parent, number, prefixes, suffix, and stereochemistry if needed. Pause now, write your answers, and then compare them on the next slide. Here are the answers. For the first structure, the answer is 1-bromo-3-methylbutane. The parent is butane, bromo is at carbon 1, and methyl is at carbon 3. For the second structure, the answer is but 2 in 1. Oh. The OH group controls the numbering, so the alcohol carbon gets carbon 1, and the double bond starts at carbon 2. For the third structure, the answer is N-methylpropanamide. The parent is propanamide, and the methyl group is attached to nitrogen, so we need the N label. If your answers were wrong, check which step of the algorithm broke down. This final roadmap is the whole lesson in one slide. First, find the Boss functional group. Second, choose the parent chain or ring. Third, number correctly using priority. Fourth, add substituents and prefixes. Fifth, add unsaturation and the correct suffix. Sixth, add stereochemistry last if the drawing gives enough information. The main message is simple. Do not memorize names randomly. Follow the same decision path every time. Organic nomenclature gets much less scary when you treat the name as a code instead of a giant word. This lesson was built from an IUPAC-centered rule hierarchy, with teaching cross-checks from sources like OpenStax, chemistry library texts, PubChem, and chemistry education resources. The most important thing to remember is that official rules are the authority, but good teaching examples help make the rules easier to apply. The next best lesson after this is functional group priority, because that is the step that controls so many naming decisions. If you understand priority, parent choice and numbering become much easier. In the next video, we can slow down and build that ladder from the ground up.